we will start the unit number 3, finite element method, in that part number 4. So already we have seen the stiffness matrix and the steps of solving the problem of FEM. So firstly we have to discretize the problem into number of elements, then find the stiffness matrix for each element, then assemble the global stiffness matrix, then load vector, then apply the boundary condition. After that, to find out the displacement, then stress, strain, etc. So these are the simple steps of any FEA problem. So let's start taking the problem on a simple spring problem. So the difference between the spring and the other step rod or the truss problem, that in spring problem K is directly given, right? So K is nothing but the stiffness of the spring, but in step bar or the other problem, so K is we have to calculate firstly and then we have to write the K. So this is the problem. So this is a wall, so spring it attached. So this is the first spring, so that first spring is treated as a first element, second spring is treated as a second element, and third spring is treated as a third element. And this first point is a first node, this is second node, third node, and fourth node. So this spring is attached between two fixed part, right? So that means node 1 is fixed and node 4 is a fixed one, and the force P is applied at the point 3, right, or node 3 we can say. So here K1 is given 100 Newton per mm, K2 is given 200 per Newton per mm, and K3 is 100 Newton per mm, and P value of P is given 500 Newton, and U1 and U4 as we can say displacement at node 1, so that means it is a fixed one, okay, constant, and U4 is this point is fixed. So let's start the solution. Or we have to find out firstly global stiffness matrix, then displacement of node 2 and 3, then reaction forces at node 1 and 4. Reaction forces means the reaction which is, because it is a fixed one, and where there is a problem or there is a part fixed one, at that time reaction is generated due to the applied force. Okay, so in the SOM we have studied that. So in reaction at 1 and the 4, okay. Then the force in the spring 2. So at the spring 2 we have to calculate the force, okay. So because of this force, how much force will be shared with the node 2. So this will be the output. So firstly we will start the stiffness matrix. We have already learned that how to write the stiffness matrix. So K, so for element 1, K1 minus K1 minus K1 K. So K1 is given, that is 100 minus 100 minus 100 100, okay. So this is for element 1. Same way for element 2, K is K2 is given, that is 200. So put the value 200 minus 200 minus 200 and 200. So same way for 3 element, 100 minus 100 minus 100 and 100. So these are the 3 stiffness matrices. Now these 3 elements we have to combine into a single stiffness matrix, that is a global stiffness matrix. And how to add these 3 matrices we have already studied. So simple way, we have to convert all the elements into 3 by 3 matrix, and by using the connectivity rule. So this is 1, node 2, node 3 and node 4, okay. Now if you consider this one, element 1 is connected by node 1 and 2, right? Element 2 is connected by node 2 and 3, and element 3 is now connected by element 3 and 4. So by using that rule we have to form the global stiffness matrix. Now element 1 is formed by node 1 and 2. So for that we have to write down the first row, first column, second row and second column. So 100 minus 100 minus 100 and 100. So element 2 is connected by node 2 and 3. That's why second row, second column, third row, third column, right? Because node 2 and 3, that's why second row, second column, third row, third column. So that's why here 100 already written here, plus 200. So 200 for element 2 stiffness matrix, minus 100 minus 200 plus 200, right? Same way for element 3 stiffness matrix. So element 3 is connected or is having node number 3 and 4. That's why row 3, row 4, column 3, column 4. Same way 200 plus 100 minus 100 minus 100 and 100. So if you calculate this matrix, so it will be like this one: 100 minus 100, 0, 0, minus 100, 300, minus 200, 0, 0, minus 200, 300, minus 100, 0, 0, minus 100 and 100. So this is a global stiffness matrix for element 1, 2 and 3. After that we have to form the equation. So that is a K into U is equal to F. So that means K is a stiffness matrix, U is a displacement matrix, and F is a load matrix. So U1 as displacement at node 1, U2 displacement at node 2, U3 displacement at node 3, and U4 displacement at node 4. Now this is the displacement matrix. After that there will be a force matrix, global load vector, we can say global load vector. So now if you consider at at node 1, now you can refer this diagram. At node 1 there will be a reaction, right? That's why it is, we have to calculate the reaction force because it is a fixed one. So we have to write down there F1. There is a zero load acting on node number 2, that's why there will be 0. At node number 3 P is acting, and node number 4 F4, because we have to calculate the reaction here also. So same way here F1 force at or the reaction force at node 1. At node 2 there will be 0 because no load is acting on that. We have to calculate that, and we will laterally calculate that. P is acting already given, and F4, that is reaction force at node number 4. Now applying the boundary condition. Now boundary conditions are given that at node number 1 and 4 there will be a constant, right? So that means at node number 1 and node number 4 displacement will be 0, right? So remember that, because boundary conditions are very important one. So displacement will be 0. That's why U1 is equal to U4 is equal to 0, and that's why to apply that boundary condition U1 is 0. That's why row 1 and column 1 is equal to 0. That's why just delete that column and row. Also U4 is equal to 0 also. That's why column 4 and row 4 we have to delete. Remaining will be your matrix. So remaining matrix will be 300 minus 200 minus 200 and 300. So U2 U3 is remaining is equal to 0 and P, right? Deleting first row first column, fourth row fourth column, so remaining will be this one. Now we have to solve this. So after solving this you will get U2 U3 is equal to P divided by 250 and 3P divided by 500. Now we know the value of P. Value of P is given, that is 500. Just put value here. So you will get 500 divided by 250, 3 into 500 divided by 500, 500 get reduced. So remaining will be 2 into 2 and 3. So U2 is equal to 2, U3 is equal to 3. So that is a displacement at node number 2 and 3, right? Because node number 1 and node number 4 are fixed one, so there will be 0 displacement. Now we have to calculate the force, reaction force at node number 1 F1 and node number 4 F4. If you put this value U2 and U3 in equation 4, right, put this form the equation 100 U1 minus 100 U2, 0 into U0, 0, is equal to F1. So value of U1 is 0, that's why it will be 0. U2 is equal to 200, right? So it will be F1 is equal to minus 100 into U2. So U2 is known, that is a 2, right? So just 100 into U2, that is minus 200 Newton. So that means reaction force is 200 Newton, and that minus sign is due to that there will be a opposite direction, that's why there will be a minus U2, minus 200. Okay, so in opposite direction, minus x direction, that's why it is a minus 200. So same way, put the value of U3 in the equation, okay, here. So you will get F4 is equal to minus 100 U3. U3 is given, that is a 3, just multiply by 3 into 100 minus 300. So these are the reaction forces at node number 1 and node number 4. Now lastly we have to calculate the force at node number 2, right? So just form the equation. This equation is given, okay? So 200 minus 200 minus 200, 200, ui uj, consider ui and uj. So I is 2 and j is 3 because of displacement value are given. So put in that value, so you will get minus 200, 200, okay, u2 u3. So just multiply this, you will get 200 Newton. So that is force at node number 2. So this, in this way, simple problems are given. So this problem can be asked for the 8 marks, 6 marks also, okay? So simple problems are there. So next problem will be on simple one element, okay? You can see here and take down this problem, you can solve easily, okay? So just overlook, I have already solved this matrix element stiffness matrix. So that is a problem for not a spring, but it is a bar problem, okay? So in next part we will solve this problem. Thank you so much.